Welcome to another episode of Calculus with Chris. Today we'll be looking at section 1.3, which goes over functions and their graphs. Again, we've got our problems you should try for in class today. So for 59, what this means is try parts A, B, and C. You'll do parts D, E, and F with your homework assignment. Also, we've got our keywords listed here at the top. And what I've also listed here is sort of our big function headings, so you sort of see what we're going to be reviewing in this video. So we'll briefly go over functions and function notation, review a little bit about domain and range, talk about this idea of one-to-one, which will be very important for us in the next section, talk a little bit about graphs of functions, classification and combinations of functions, and finally, everyone's favorite, function composition. I do apologize in advance, this video does get a bit long, there's a lot of vocab words to review. None of them are too bad, but it just does take some time. Alright, let's get started. So the first thing we want to look at is this idea of a function. It's going to be a basic idea we're going to use throughout the course, and so as I've said, lots of vocab. But a function from the set x to the set y is a rule that assigns one element of x to exactly one element of y. X will be called the independent variable, y is the dependent variable, and we write functions as f from x to y. So let's start by looking at an example of this. So for example, if we look at the question, what is the main reason that your girlfriend broke up with you? This is a function. So of course the independent variable in this question are all of your x's. You know, if someone came up to you and asked you this question, you would have to say, well, which girlfriend would you mean? You'd have to specify an input. And then the dependent variable or output is going to be the reason why. It's going to be sort of the answer to a question. So you always want to think of a function as sort of a question that takes an input, and the output is the dependent variable. And here's a real concrete example of this. Here we've got different x's, Jamie, Emily, Susan. I apologize if anyone has the same names in class. These are made up. And the reason why they broke up with me, Jamie said I played too many video games, Emily said I spent too much time with my friends, and Susan also said too many video games. Now, the big thing with functions is this is okay. These repeat answers, these repeat y's, are just fine. What we want to make sure is that each input, though, only has one output. A girlfriend can't give two reasons over here for breaking up with me, because the question was, what is the main reason? If I wouldn't have said main reason, then it wouldn't have been a function. So just to reiterate, it's okay, we can have the same output from two different inputs. Now let's look at a more mathy example. So we all learned a long time ago that if you have yourself a square, and you decide, so that is a square even though it doesn't look like it, and you decide to label the side with length s, formula for getting the area of the square is just going to be s squared. And in question form we have this here. What is the area A of a square with side length s? So again, our s here is our independent variable, and the answer to this question, the actual area, is going to be the dependent variable. Now one of the ways we write functions usually is we usually write this to indicate that we have a function. The a of s over here indicates that it's a function, and it indicates exactly what we're going to call these things. The s here is going to be our input, so our independent variable, whereas the a depends on whatever we put in, so this is our dependent variable. Now it's also important to note that we can write functions in many different ways. Each of these expresses the same idea. This is a function f of x, x squared, g of t equals t squared. They all mean the same thing. Take your input and square it. Another thing we want to do is to be able to evaluate abstract functions and remember what they mean. So let's look at this here. So we've got a function, f of x equals x squared plus x, and we want to figure out f of 3 and then f of b minus 1. Now these aren't so bad. What this f of 3 means is I simply need to go down, and everywhere where I had an x, I replace it with a 3. So the first x squared becomes 3 squared, and the last x becomes 3, and then I'm off to the easy world of arithmetic. 9 plus 3 equals 12. So 3 was our input, 12 is our output, not a bad function. Now part 2 is what we're going to be doing a lot more of in class, and hopefully you gain some experience doing this in your algebra course. We want to now put b minus 1 into our function. Well, what this means is we need to go down, and everywhere we had an x before, we'll put parentheses, so that we leave room to put that b minus 1 in there. So we just replaced all of our x's with b minus 1, and now we're off to do some algebra here. So here we remember that b minus 1 really means b minus 1 times b minus 1 plus a b minus 1. So off to algebra. Let's see, b squared minus, hopefully there's 2b's, plus 1 plus b minus 1. And if I didn't screw anything up, this simplifies down to b squared minus b, and I think that's it. Overall, the big thing here is this isn't so bad. All this notation means is you replace all of your x's with b minus 1 or 3 or whatever happens to be in there, and then you go ahead and simplify. So our last big idea from functions before we move on to this domain and range idea is a good non-example. A non-example of a function is what is the name of your sister. Now this seems okay. It seems like we'll be fine and make this a function. In this function we have an independent variable, we have an input. We can even use my name, Chris. The problem occurs with our outputs. When we try to specify our outputs, we run into problems here because we've got two different outputs. I have two sisters, Jessica and Amanda. So we fail in our function rule part, the function that we assign everything from the set x to the set y, where from one element of x to exactly one element in y. Here, I'm trying to send one x to two y's, and that just doesn't work. That doesn't make a function. So now we're on to our next big vocab word, the domain and range. So the domain of a function is going to be the set of x, the set of all inputs, whereas y is the image of x under f, commonly written as f of x equals y. This is also called the value of f at x. The range of f is the subset of y and consists of all of our outputs. So the domain, really the key here is to see that the domain is all of your inputs, and the range is all of your possible outputs. So let's look at an example of this. So here we have ourselves a function. So it's a perfectly good looking function. F of x tells us our input is x. Our output will be whatever number we get when we put x into this expression here and take 2 over x minus 4. And our domain is being told to us here that it's going to be any numbers from 5 to 10. So this really tells us our domain, what numbers we can put into this function. Now, we're smart, so we don't always need to be told what to do, but sometimes we need to figure out what to do. So this next function, g of x, is a little different. It looks the same. G of x says x is your input, take 2 over x minus 4, but here we have no domain given to us, so we have to figure out that the domain is going to be everything except x equals 4. We can put any number we want in here. We can put in 3, 7, 12, whatever, as long as we don't put 4, because 4 would cause us to divide by 0. So when we go about finding the domain of functions, we want to be careful of two things. First of all, no dividing by 0. You've been avoiding dividing by 0, hopefully, since you're in elementary school. And also no square roots of negative numbers. You can take the square root of negative numbers, you get complex numbers out, but that's for a different course. In this course, we're going to be mostly caring about real numbers. That'll give us enough problems. So now let's look at a few more examples of this. So we are going to go ahead and try to find the domain of this function, g of theta equals sine of theta. So for those who are great at Greek letters, that's a theta in there. And we're going to find the domain and range right away. Now, the thing to remember here is this is a good trig function. Trig functions can take all numbers as inputs, at least sine can. So this means that our domain is going to be all real numbers. Now you can write this however you want. You can get really fancy and write a fancy r. You can write this goes from negative infinity up to infinity. You can write all real numbers. Any of these work really well. We also want to think about what the range of this function is, and for that we're probably going to need to look at the graph. So here's a partial graph of this function, And the key thing to remember is that this function just keeps going to the left and right if we were to zoom out. And so since our function has no breaks in the graph anywhere along the horizontal, our domain is all real numbers. We can put anything in. Our range, however, is going to be just these numbers here that we can specify vertically. That is, what output numbers do we get here? And we can see here that our range is going to give us all values from a low down here of -1 all the way up to +1. So we can specify this using bracket notation. We can use this notation here with, of course, equalities because we actually get the numbers. And that's what these brackets mean. We actually hit those numbers. Either one of these is fine as well. If you prefer the brackets, the inequalities, both work. So we have a domain all real numbers and range -1 to 1 including those numbers. So now we're going to look at an example of everyone's favorite functions, piecewise functions. So this function has two pieces. The first one says that if your input is greater than or equal to 2, use the first part of the function, use the first rule, 3 over x minus 4 plus 6. If x is less than 2, we have to use the second part, which says to take the square root of it. So let's look at the graph again. So we'll start by trying to find the domain of this graph. So the domain, remember, is all numbers we can safely put into this function. So this function has two parts, and so if we look, we see that the first part of this function is the 3 over x minus 4 plus 6, and this function is going to be great as long as we're careful that we don't let x equal 4. So we want to make sure that we don't put 4 in here because that'll cause us to divide by 0 down here in the denominator. Also in the square root of x part, well, we don't want to take the square root of a negative number, so we need to make sure that x is always greater than or equal to 0. We don't want to take the square root of a negative number. And so what this means, putting this together, is that if we were to draw a number line here, and if we put a mark here at 0, well, then what happens here is we can't use 4, so 4 is out, it gets a little open circle, and then we don't want to use anything down here less than 0. So what this leaves for us in our domain is we can use numbers starting at 0 up to the number 4, not including the number 4, that's what the parenthesis means, and then we can again use 4 all the way out to infinity. So this is going to be our domain, and we can see this over here also in our graph. If we look at our graph down here, what we've got is we've got outputs anywhere from 0 up until 2, we really do get an output there, all the way over until 4, and we've got a break in our graph, and then we start our graph over at 4 and keep going. So this tells us that numbers between 0 and 4 to infinity are safe to put into this function. As long as we're looking at this function, we should also think about, well, what's the range of this function? Now the range is something that you'll almost always need to look at the graph to figure out. In this case, if we looked at our function, if we were to zoom out on our graph, we'd see that our graph starts all the way down. It can get any number, any negative number will have an output on it. And we keep going up until right around here at 5. And then there's the break in our graph up until 6. And then there's another break in our graph. I misspoke. This is at 4.5. I'm sorry. So what this means is that our range is going to be all numbers from negative infinity all the way up to 4.5. We actually hit 4.5, and then we don't actually ever hit the number 6, but we go from 6 to infinity. So these are all possible outputs for our function. Our next vocab word is one-to-one. We're going to say a function from x to y is 1 to 1 if for each y value in the range there's exactly one x value in the domain. That is, we don't want repeats. The big key word here basically is unique output from our function. So let's look at an example. So a good example here is, what is your student ID number? In this case, the independent variable is a student's name, and the dependent variable is the student's ID number. That's your output. Since there's no repeats of the output of this function, we're not going to put two different students in and get the same student ID number. This is going to be 1 to 1. We also want to look at a non-example. the question, where did you go to college, is not going to be one-to-one. We still have a good independent variable, which is a student's name. It's still a function because a student will usually only want to say one thing. They only went to one college, and for most people watching this is going to be Doane College. But since there's a possibility of repeated answers, this is not one-to-one. That is, if you ask Jim the question, he'll say Doane. And if you ask Tom the question, he'll also say Doane. And since they said two different answers, this function is not one-to-one. We're not sending one x value to the same thing. We get multiple of the same outputs. So here's a little assignment for you to do. Look at the bottom of page 22 in your textbook. There's a whole bunch of graphs on there that you should know by heart. You should know their names, you should know how to graph them from their graph. You should say, oh well, that kind of looks like x cubed or something like that. You should be pretty good at looking at these and figuring out what they are. I would suggest memorizing them. Perhaps, we'll have a quiz on them or something, so it might be good to know. Let's suppose we have two functions. We'll call them f and g. Well, we can combine these functions in several different ways. You combine them basically the same way that you learned how to combine numbers ages and ages ago in elementary school. Well, one of the first things you probably learned is how to add, and so that's called sum. So we can add two functions and write it like this, which means take the function f of x, add it to the g of x. So you write them right next to each other, with an addition symbol in between. And then you can always simplify and add stuff if you feel like it. I'm not going to be too big on simplifying here. I guess this is going to be x squared plus 2x minus 6, as long as I did nothing wrong. Alright, after adding things, you can guess the next thing we can do with functions. You guessed it, we can compute the difference of two functions. We can subtract them. So it's very similar. We subtract, we replace addition with subtraction, and we're good to go. Now a little later, you probably learned two more things you can do with numbers. And those last two things you learned was, of course, multiplying, which product is a fancy word for, and dividing, which we call the quotient. And it's pretty much what you would expect. You take the product of two functions, you multiply them together, you take the quotient, and you divide them. Now functions have one fancy thing you can do with them that you can't do with numbers, and it's called function composition. Now if we have two functions, f and g, what we can do is we can form what's going to be called the composite of the functions, the composite of the function f with the function g, by basically putting one function as the input of the other function. And the domain of this new function is going to be a set of all x in the domain of g, such that g of x is the domain of f. That is all numbers you can put in and keep putting in to go all the way through the function. I think this is best understood, of course, with an example. And what you hopefully see from the example is that this is just a fancy way to chain two functions together to get one function in the end. So suppose you get the idea that you're going to go and paint some squares. You've got some squares, they need to be painted. So you know two things. You know that a square with side length s inches has area a of s equals s squared, because, well, they're squares after all. And you also know that if a square has area w square inches, then this is the function p of w equals 3w, tells you how many ounces of paint you're going to need. And you want to know how many ounces of paint to buy based on how big your square is. Well, the long way to do this is to say, well, I've got a square, and it's 2 inches long, which tells me using my a function, I take a of 2, and I get 4 square inches. And then from here I can use my p of 4 function to compute 3 times 4 is equal to 12 ounces of paint. So the a function here tells me how to get from inches to square inches, and the p function tells me how to get from square inches over to ounces. And what we're going to do is we're going to compose these functions, that is, put them together in order to just get one big function that goes right away from inches all the way to ounces. And this is going to be the p of a of s function. And so this function is going to end up being 3 times s squared. Now, we're going to go over another example where we go through the algebra of this, but this is the basic idea, is that what composition allows us to do is it allows us to combine two functions to make one much easier function. Because now what we can do is now we can just say, give this new function a name h. If we take h of 2, well, this is 3 times 2 squared is equal to 12 ounces. So in this example, what we want to do is algebraically find the composition f of g of x, where f of x is x squared plus 2x, and g of x is equal to x plus 2. So step 1 is just remember that to find the composite of a function, f of g of x, so this fancy symbol means composite, is equal to f of g of x. We're going to make g of x the input to the f function. And since we're making g of x the input of the f function, we're going to replace g of x everywhere we see it with x plus 2, so g of x becomes x plus 2. By definition of our x function, what we want to do is we take these x's in our f function and we replace them with our new input x plus 2. So x squared becomes x plus 2 squared, 2 times x becomes 2 times quantity x plus 2, and now we're into some simplifying. So we first simplify by multiplying everything out, and then we combine it all. And so we have our final answer, x squared plus 6x plus 8. Now what you should do is take a minute to try on your own and find g composed with f, that is, compose them the other way. Pause the video, then I'll show all the steps you should have followed. So here we go are all the steps you should have followed. If everything went smoothly when you substitute all the way through, you get x squared plus 2x plus 2 as your final answer. The big takeaway is note that these are different. That is, order of composition really matters. So we've done a lot today, a lot of review of vocab words that you've probably spent several years learning in middle school and high school, maybe even before and after, but here they all are. So remember, what you should do now is you should go and try these problems, bring them to class, take the quiz online, and also post a question. Thanks.